Hello everyone, I am Dattatreya Nikam. Welcome you all on our channel eFunda for new day, new topic. And our today's topic is industrial control system, which we are going to present in parts. Are continuing with the topic of distributed control system design guidelines part 23A. And if you are new to our channel, then please visit to our channel and watch all the videos created related to various topics of engineering, fundamental, telecommunication engineering, procurement engineering, instrumentation and control engineering, deliverable in interview related questions, and renewable energy. And don't forget to subscribe to our channel and also press the bell icon to get the latest notification on upload of our new video on our channel eFunda. So let's begin with our today's topic, that is a distributed control system design guidelines part 23A. Introduction to distributed control system, that is a DCS. A distributed control system is a platform for automated control and operation of a plant or industrial process. A DCS combines the following into a single automated system, which mainly includes human machine interface, that is HMI, logic solver, historian, common database, alarm management, and a common engineering suite. In a control system refers to control achieved by intelligence, that is distributed about the processes to be controlled rather than a centrally located single unit. Utilizing the DCS for remote monitoring and control of the industrial processes can offer a variety of benefits such as improved process efficiency and quality, enhance process safety and reliability, reduce operational and maintenance cost, and increase operational and business intelligence. And for better understanding of this DCS control system, or rather instead of DCS one can say the various types of a control system, one can refer to our video which we have created on our channel, that is a overview of a control system part 11, where we have covered DCS, PLC and a SCADA system in detail. Now DCS system design guidelines, we will see how the typically design guidelines are useful and how it has been listed. First, start or complete your project IO count or IO summary. Second, identification of physical areas of IO concentration and other systems. Third, identify IO areas to include on the network structure. Fourth, review system specification from customer. Fifth, identify the requirement for a BPCS or safety systems or both. Sixth, identify redundancy requirement at a system, network and hardware level. 7, scale out of a basic network structure which identifies system to be connected at each level. 8, identify other subsystems to be connected, that is vendor packages, business systems and other sites as well. 9, finalize the preliminary hardware and network structure. 10, study of documents like cause and effect diagram, that is a CED, and a control philosophy. List the logic requirement and a soft tag requirement. 11, identify and specify the HMI SCADA requirement, including graphics, reporting and other system connections. 12, review of the hardware design with detailed BOM and cabinet design. 13, review of software, graphic, reports and system interfaces. 14, witness a hardware FAT, that is a factory acceptance test, often witnessed along with the customer. 15, witness an integrated software FAT, that is simulation is required. 16, receive IRN and approval of IRN to enable vendor to ship system to site and install as ship document. 17, system installation and commissioning, one can refer to the picture how the DCS system is being installed. 18, system IO testing from field to graphic. 19, interface testing. 20, area by area testing. 21, detailed SAT, that is a site acceptance test, always witnessed by the customer, system handover to the client. 22. Receive as-built document incorporating the markups given at a site. 23. Operator and maintenance training is required for the operator who is going to handle the DCS system. DCS system architecture, one can refer to the figure where one can see the interface from field level to the direct level to the supervisory control level, and where one can see at level 0 where plant is shown and the various types of field instrument along with the sensors are connected, and which is getting connected to the level 1, which is to the marshalling cabinet, and then IO rack, and then further it is connected to the system cabinet, which is level 2, and further at last it is going to the level 3 where mainly the supervisory level where the operator station, engineering workstations are involved to have the operation of a monitoring and a control by the operator. We will see the further details on the level basis so as to understand the DCS system architecture with the help of their guidelines. Moving on to level 1 and 2 control cabinet, and for the field instrumentation, that is the plant instruments, which we have already created separate video, one can visit to our channel and watch. Here in the level 1 and 2 control cabinets, we are going to cover the topic of type of a control cabinets which are listed below: marshalling cabinets and IR, that is the interposing relay cabinets, marshalling cabinets, foundation field bus, system cabinets and controller and IO subsystem, network cabinets, power distribution board, that is a PDB. One can refer to the another picture where we have covered the cabling from field instruments to the operator console, where one can see the field instrument which is connected to the junction boxes, and further junction boxes is connected to the marshalling cabinet, and further it will go to the system cabinet, and finally it will reach to the operator for their necessary information and action. Similarly, for better understanding, refer below the loop diagram where the details are covered from process area, junction box, the marshalling cabinet and system cabinet, where the branch cables, multi-pair cable, cross ferruling or cross wiring to the isolator, barrier and prefabricated cables to the IO cards are shown. On this topic we have already created detailed video. One can refer that video, that is the instrumentation control panel, that is part 14A, and there you will get all the details related to the control cabinets. Level 1 and 2 earthing scheme, one can refer to the picture where the cabinet are shown, where the system earth, instrument earth are connected, where the building safety earths are shown and the building safety instrument earth bars are shown, and respective connections are done with the help of design or size cable, that is a 25 square mm and 70 square mm. Now one can refer to the picture for a better understanding where the earthing to the isolated bus bars or bus bars are shown, and similarly for the field instrument. And to better understand, one can refer to the table where we have covered instrument earth, electric earth, reference earth, clean earth, signal earth is shown or used by the green color, and allowable resistance is a less than 1 ohm, which is normally control system vendor value recommendation, and the purpose of this is to provide a low impedance path to the noise current induced by the RFI or EMI, which may result in the induction faulty unwanted noise signal into the analog signal. That is the reason shield of a single pair or a multi-pair analog signal cables are connected to this instrument earth. Intrinsic safety earth, that is the IS earth, used with a green color, and similarly less than 1 ohm value, which has a direct connection between the earth terminal of the shunt diode and the main earthing terminal of the electrical supply. Safety earth, that is AC, dirty earth, protective earth, electrical earth or power earth, used with a green with yellow strips based on the electrical design specification contract. This gives the allowable resistance, which understand earth faults pose safety risk to personnel, also may lead to safety hazard such as equipment malfunctions, fire and electric shock. That is why we need to have the electrical earth or safety earth. Level 1 and 2 types of IO configuration one can refer, that is the type configurations are listed below. Local IO racks and without redundancy, local IO rack with redundancy, decentralized controller, that is remote IO, wireless network. One can refer to the entire control system IO configuration picture, where one can see the mounting grain where all the instruments or equipment or system related components are installed, where the bus adapter, interface module, IO module, server module, plug-in connector for power supply, terminal block, power bus bar, carrier module for the interface modules are shown. And similarly on another picture where one can get the detail how the IO builders are connected, that is IO builder up to some many specified IO and their distribution, redundant IO, distributed IOs for the single IOs, and price comparison if any. This is how the details of the types of IO configuration has to be covered as part of the DCS system design. After level 1 and 2, now level 3, operating and supervisory control, where one can refer to the picture we have used from the internet source, where one can see the level 0, level 1, level 2, level 2, 3, level 3, level 4, level 5. Various levels are shown for SCADA, DCS or hybrid systems, mainly including the system component as well as including the cybersecurity related equipment. For this we have going to understand mainly the engineering workstation, that is EWS, which allows you graphically configure object oriented control logic and simultaneously generate HMI graphics. Now operator workstation, that is OWS. HMI includes a vast variety of tools to help you to monitor and control your process. No programming or interface with any other software packages should be done to get trend and alarm viewing, diagnostic, command window, faceplate and other utilities which you can monitor and control for your project. After level 1 and 2, level 3, operating and supervisory control, which includes instrument asset management system and integrated real-time IAMS for instrumentation shall be considered as part of the DCS, which can provide maintenance capabilities based on the collected diagnostic information of the foundation field bus and hard instrument, control valve, on-off valve, etc. Similarly, alarm information management system. The alarm information management system aims shall be fully configurable system capable of processing all the alarms in appropriate manner to maximize the information provided but to minimize the number of alarm displayed. OPC server should have capability of bidirectional communication for reading from and writing to DCS. Third party OPC client should be able to establish such bidirectional, that is read and write communication with the DCS through these DCS gateways. Historian server system shall consist of a history station for DCS safety PLC system, which is used primarily for storage of the history data, tags, that is analog IOs and digital IO as configured in a system should be historized for minimum period of 6 months at the rate 1 second or as specified by the customer during the system specification. Third party interface can be established using Modbus RS-232 point-to-point communication, Modbus RTU, that is RS-485 daisy chain communication, Modbus TCP/IP communication, wireless hard ISA 100.01, Profibus DP PA OPC connectivity, etc. Now after seeing the detailed DCS system guidelines, where we have covered level 0, level 1, 2, level 3 details, now we have reached to stage where we will see the DCS control system vendors or the manufacturer. One can refer to the table. We have listed down some of the DCS vendors which are popularly known for providing the DCS control systems are as follows. ABB system 800XA, country of origin is the Switzerland, Honeywell Experion USA, Siemens PCS7 Germany, Emerson Delta V Ovation USA, Yokogawa Electric Centum VP is from Japan, Allen Bradley Plant PAX USA, Valmet DNE Finland, Schneider Electric, EcoStructure Foxborough, that is France, Mitsubishi Electric, PMSX @Pro, and PMSX Micro is from Japan, Hitachi, HIACS Japan. These are some of the vendors which are listed and popularly known for providing the distributed control system. This is how we have tried to cover the DCS control system design guidelines for you, and keep watching the videos related to these topics and get the details of the DCS control system. With this, we are concluding on our today's topic, and you can find our channel details as follows. If you are new to our channel, that is our YouTube channel eFunda, then subscribe to our channel eFunda, and don't forget to press bell icon to get latest notification of upload of our new video on our channel eFunda. Similarly, you can follow us on a Instagram page. Similarly, you can follow us on our Facebook page as well. And keep watching our channel eFunda for various topics related to engineering and a project. With this, we can assure you this will help you to better your understanding on engineering and a project topic. Keep watching our channel eFunda. Thanks. Watch our channel for new day, new topic.